Thank you. Thank you, DK. I was afraid it's going to be long. So basically, I'm Gilad. I manage HPC at Mellanox. Been with the company for 19 years, more or less. Started on the R&D side of things, and then moved to the dark side of engineering, and started dealing with the business side and technology and so forth. So thanks for having me here, DK. And I'm going to discuss the latest around the InfiniBand In-Network Computing capabilities and the things that we're looking to do in the future. So first, starting from a high-level perspective, and this is the area that we do focus, or put most of the focus in the recent years, with the motivations to move or enable the move of the data center from a CPU-centric approach, where everything's done on the CPU, to a data-centric approach, where the major element in the data center is the data, not the CPU. And in that sense, you want to move the compute to the data instead of moving the data to the compute. And by moving the compute to the data, you can actually do things much faster and overcome performance bottlenecks and enable to analyze greater amount of data and so forth. And in order to enable the data-centric architecture, the missing part is to move computing capabilities into the network as well. In a sense, compute capabilities exist in the CPUs also for the CPU-centric architecture. So the missing part is actually moving compute to two areas, essentially. One of them is to the network, and the second part is for edge computing, which I'm touch a little bit at the end of the talk. So as part of moving more smart element to the network, we actually look on the network in different kind of pillars. And in every pillar, you're trying to bring interesting elements as part of accelerating data analysis. The first pillar is the connectivity side. And not everyone knows that you can actually impact the application performance by building different kind of network topologies. InfiniBand, one of the key advantage, I think, in InfiniBand is that it was born as an ultimate SDN fabric before people knew what SDN is. You can program routing, and you can build any sort of topology that you want. So this is one thing that you can do with it, and actually building a different topology may or can impact the application performance and the scaling of what you can achieve. Most people build fat trees, and fat trees is a good topology, and it gives you low latency and high performance and so forth, and nicely support broad range of applications, but it's not the only option. If you're building something for stencil applications, you probably want to look into toruses, not into fat trees. HP or SGI has hypercubes, for example, and then 2 years ago, from Mellanox perspective, we also brought the Dragonfly Plus, which is an enhanced version of Dragonfly that enables to achieve same performance levels as fat trees, but gives the ability to actually seamlessly scale over time. So there is multiple things around that. On the network pillar, and this is, I think, where most of the Mellanox focus was on the early days, the idea here is to move first all of the network functions from the CPU to the network. There is no reason for the CPU to deal with network transports, for example. You can do it on the network and save a lot of CPU cycles. So this is where we started with moving the entire transport protocol to the network, and then did the RDMA, and a few years after brought the RDMA also to GPU communications with GPU direct RDMA, for example. Recently, we also had another capability which is actually aiming on resiliency of the fabric, which is called Shield. And I'll touch a little bit about that and how it works. And then the latest, that's part above it. And then we continue also to enhance adaptive routing and congestion management and congestion control and so forth. And there's new things that we brought into the HDR technology that we look to demonstrate on Frontera system, for example. The third one is the communication pillar, and this is where we talk about MPI. and the rest of the communication frameworks. And our mission in that area is to try and move as much as we can from the data path of those communication frameworks into the network. So actually have engines on the network that be able to execute as much as possible from the data path of the communication frameworks. DK mentioned SHARP, for example, which is ability to run data reduction, so data aggregations on the network, doing tag matching on the network, and then you can do rendezvous protocol on the network and so forth. One of the recent additions to the InfiniBand technology and also to Bluefield is actually have the network adapter ability to pretend to be any other PCI Express device that you can find in the system. There is a compute engines within the network adapter that can capture everything that comes from a PCI Express interface and do anything that you want with it, and then do it something back and send it back. So with that capability, the NIC or the network adapter can pretend to be any PCI Express device. One example is to pretend to be an NVMe flash. So one of the things that people that looking to get faster storage, what they do is bringing more flash to the server. And when you bring more NVMe or flash to the servers, you get faster storage and everything is cool. The only thing, it is expensive. And then people start thinking about, okay, instead of putting flash on every server, I may want to take the flash out and create JBOFs and do NVMe over fabrics. And then run remote NVMe and get almost the same performance as a local NVMe. The only problem with that approach is that the application or some software needs to be aware that there is no local NVMe, but there is a remote NVMe. What we do with the new capabilities is actually having the network adapter pretend to be a local NVMe device. And what's happening in that side is that the application thinks that there is a local NVMe, and it does send NVMe or local NVMe commands to the server. The network adapter captures those commands, change them to NVMe over fabrics, goes to a remote storage, does what it does there, get the response, and then change it back to local NVMe response. So the application thinks that there is a local NVMe device by actually you're running over a remote. So this is one example. You can think about the network adapter as an entity that can emulate any PCI Express device that you can think about and actually go over the network and get resources somewhere else. So that's something that we'll see more development in the next months or year to come. And the last part is on the application space, where if you have compute engines on the network and you have configurable logic on the network and you have memory on the network, then you can start thinking about moving some of the workloads to actually be run on the network, not just on the CPU. You can think about the network as an entity that enables or provides distributed computing across a data center, or distribute memory across a data center. So now you can break a workload, and part of the workload can run on the CPU, and part of the workload can actually run on the network in parallel. So that's what we're working on. So if I'm taking 4 examples here, the first example I wanted to show you is SHARP, which I think is part of the information we showed before. SHARP is a name for a technology that builds compute engines that sits on a data path on every switch. And then compute engines can look on the data, not just on the headers. So the switch is an entity that's not just steer data between one port to another port, but it actually looks on the data, and it can do data arithmetics on what's going or what's passing within the switch. And the compute engines can do any data manipulation that you can think about, integer and floating point and so forth. Now what we do with that is that we program that engines to do a data reduction or data aggregation. So instead of doing all reduce on the CPU, you can do the all reduce on the network. So the host will send their pieces of information, and actually the switches will be the ones that do the data aggregation. It goes to the second layer of switches, which will do the aggregation among the switches, and then they do the broadcast back, and all the host gets the results back. the key or the nice thing around that is that it gives you flat latencies. So we all know is that you're running a reduction operation, the more processes you add, the higher latency you get. And when you run it on the network is not impacted, or the switch doesn't really care how many hosts exist. In that case, it gives you flat latencies. So those are two results of 128 nodes of a system doing 8 bytes or 128 bytes of all reduce, or 1 kilobyte or 2 kilobyte of all reduce. Dashed line is latency running everything on a CPU, and then the solid line it's using Sharp for doing the reduction. This is the results from University of Canada. They have a 1500 node system there. The right side is running a reduction operation on the entire 1500 nodes, 40 processes per node, 1 process per core. So 60,000 MPI ranks, and you can see the latency running reduction on the CPU versus latency running reduction on the network on the various message sizes. Now, reduction, it's not just for kind of core HPC, it's also the critical element in doing deep learning. And what we're doing now is working with the folks with NVIDIA to actually incorporate Sharp into Nickel or Nickel 2. So in Nickel, you can run Nickel on a tree base or Nickel on a ring base, and this is doing this is performance results on 4 nodes. 1 adapter per node, 2 adapters per node, and the green one is 4 adapters per node. Then you can look on all reduced throughput. So it's not the latency that matters there, but the throughput of the reduction operation. So this is the gigabyte per second of all reduced throughput doing Nickel 3, and then doing ring, which is better. And then when you combine Sharp, you actually get much better numbers. So what's the impact of that on the applications themselves? So those are our first results that we did release, running ResNet 50, so going all the way to the application. And then did testing on 8 nodes. So we did 8 nodes at 16 GPUs, and we had more GPUs, so actually we did 8 nodes and put 22 GPUs. So some nodes had 3 GPUs, some nodes had 4 GPUs. Running ResNet 50 on TensorFlow, without Sharp, which is the yellow, and then with Sharp, which is the blue bar. And then on 22 GPUs and 8 nodes, we got 16% performance increase for ResNet 50. And the more GPUs you add, the higher the impact is going to be. So that's on Sharp. The other elements are, as I mentioned before, it's MPI Tag Matching, and this slide I stole from DK Panda. I think he presented that in a couple of slides, so I combine them together. But it does give interesting performance improvements, so latencies for the mid-size messages on the eager protocol, and then you can see a nice reduction latency for other parts of collectives. GPU Direct, that's element that we brought into the GPU systems. So InfiniBand enabled RDMA, and then with GPU Direct, we brought RDMA also to be run on GPU memory, not just on the CPU memory. It's all based on the ability to do peer-to-peer over PCI Express that enables 2 PCI Express devices to send data directly between them. And then this is, again, I stole those results from DK Panda. So looking on the advantages of GPU Direct RDMA for both latency or increasing throughput by enabling moving data directly from a GPU memory to GPU memory and not going to the host memory. Now, not everyone knows that GPU Direct RDMA, it's actually GPU Direct 3.0. So there was 1.0, which eliminates some buffer copies. And it was 2.0, and then GPU Direct RDMA, it's actually 3.0. There will be a 4.0, probably coming next year, which also will be known as GPU Direct Async. The difference is that the GPU Direct 3.0 or RDMA move the data path to run between the GPU memory to GPU memory directly over the network, but the control path is still run on the CPU memory. With Async, we also move the control path to be done on the GPU memory and not going to the CPU memory. And then it gives another performance boost. This is doing a 2D stencil benchmark, and it's a 20+ reduction in latencies. So that's going to come probably next year as GPU Direct 4.0. Quality of service, it's another aspect that's become more and more interesting recently. Typically, when you're running an HPC workload, all the users have the same quality of service. So MPI actually give the same quality of service for all the processes that are running, but you don't have to. InfiniBand gives a very enhanced capability of allocating different quality of service for different kind of workloads. So first, you can separate quality of service between storage and MPI, for example, between management and storage and MPI. And even within MPIs, instead of giving the same quality of service for any MPI job or any MPI user, you can actually give different capabilities to different users running MPI. And then you can guaranteed latencies or guaranteed throughput and so forth by allocating quality of service or different kind of quality of service for different kind of workloads. It's become very interesting when you look on a system and you're running MPI jobs and there is some storage jobs, for example, and you don't want those storage jobs to interfere or create congestions issues, for example, for the MPI jobs. That's the cleanest way to do it. Putting the storage jobs, other jobs on one quality of service and putting the MPI jobs on the another quality of service. And then you can actually get a very clean performance and guaranteed performance for the jobs. Another thing is congestion control. So congestion control exists in InfiniBand for years. This is a paper that I was part of it that was released in 2010. So 9 years ago. They did the first experiments on utilizing InfiniBand congestion control. It was done back then on QDR and DDR links, and then looked on the impact of congestions on victim flows, essentially. This is what you're trying to solve. In this case, it was one flow that went directly from one node to another node, and then there was many-to-one case here. The only thing is that the flow here and then the many-to-one share the same link. And what happened is that at the beginning, when just one flow was running, everything was good. The second flow was running, continued to be the same. But once you start hitting the many-to-one, you can create congestions that impact that flow, which is called victim flow, and then all the bandwidth goes down. And then InfiniBand congestion control enabled actually to make the right allocations and ensure that the victim flow is not getting impacted. And you can see that in the results there. We have brought more enhanced capabilities into the HDR generation that we're planning to release shortly, and I think probably TAC will be one of the first places that we're going to run some benchmarks on the new version of the InfiniBand congestion control, and we'll release numbers. Shield is a technology that aims to increase resiliency of the fabric or resiliency of the system. Essentially, it's utilizing compute engines that exist on a fabric. So now switches can do calculations and get some more understanding of what can be done. And the idea behind Shield is that in cases where you have link failures, and you can define what a link failure is. It could be a link that goes down, or a link that is throttling, or a link that his performance was degraded over time, and so forth. So when a link goes down, what typically happens in any network that exists is that there is a notification that is being created and sent to the software management, and then the software management comes and do something. It can change scheduling, can change routing, or other things of that sort. The only problem is that it takes time. So if you have a 1,000 node system, it takes around 5 seconds for software management to react. And if you have a critical MPI job that's running and for 5 seconds it doesn't get data, good chances that that MPI job is going to crash, and then you go and do checkpoint and restart. So the idea behind Shield is actually have the network be able to find the solutions within the network and not wait for the software management. Shield is a very topology-aware mechanism. It works differently on different topologies. What I did here is I took an example of a fat-tree topology, a 3 tiers fat-tree topology. In this case, we're sending data from server A to server B, and everything is nice. So one thing that can happen is that you have a link that fails when you go up the tree. And in a fat-tree topology, that's not a major issue because that switch here has actually multiple routes you can choose. So you just will choose another route immediately and then just overcome the link that failed. The more interesting problem is that when you have a link that fails when you go down the tree. And if you didn't build high availability into the network, once you go down the tree, from this point, actually there is only one path you can choose. So once you start going down the tree, you will need to discard data. And if you discard data for 5 seconds, for example, that can cause the MPI job to crash. So in this case, is the switch that detects the failure, which is the switch here, will send notifications to other switches in the fabric, so they will change routes. Now, it doesn't send data to everyone that exists, because you don't want to create storm, and then many of the switches here cannot do anything. You actually send notification to very specific switches. So for the traffic that goes down here, or if the issue is here, then everything that is above you cannot do anything. So you don't care about those switches. Actually, in a fat tree, every switch that is the same layer of the switch that detect the failure cannot do anything as well. The only switches that can change something are the switches that are one layer down. And you want to pick those switches that actually send the data when you go up the tree, which is talking about this area. So in this case, the switch here will actually create notification that goes all the way to the switch here. And this is the only switch that can change the route in order to avoid getting there. So the rerouting is going to happen here, and the switch here will do rerouting, and actually the data is going to overcome, or not going through the link that failed. The time that it takes to run something like that as a worst case scenario is 1 millisecond, not 5 seconds. So that means that MPI jobs can continue to run. We had some recent cases of systems that were built in last moment and needed to run lean-pack. And of course, when you build a system, is in the first weeks, you go through and find issues and so forth. But even though there were links that failed during the first runs of the system, we could run lean-pack without impact because of that capability. Now, it's also become interesting when you combined this capability with adaptive routing, which is the other part. So adaptive routing, it's a newish element for InfiniBand. It started in the second generation of EDR. And the reason is that InfiniBand was born as an in-order data delivery fabric. So if you do adaptive routing, you can create out-of-orderness, which means there is performance penalties. In ConnectX 5, we added the capability of doing out-of-orderness in hardware. And with that capability, we can actually run fine-grained adaptive routing on the network. Now, when you're running adaptive routing, essentially adaptive routing gives multiple mechanisms one can choose for how the switch is going to work. The switch can go and each switch can go and choose the least busiest port, or the switch can take a group of least busiest ports and do random selections between them and so forth. When you have a link that fails, and if you are going with choosing the least busiest port, typically the least busiest port of a switch will be the one that is connected to the link that fails on the other side of the fabric, because that's always going to be empty. And this is why it's interesting or important to combine shield and adaptive routing. So shield runs in parallel to adaptive routing, and actually it goes to the switches and eliminate using path of switches that will cause sending data to link that fails in other places of the fabric. This is the result of InfiniBand adaptive routing versus static routing that was done on Summit. So Summit is 4,600 nodes, but every node has 2 ports on it. So from a network perspective, that's a 9,600 ports or network. What was done there, it was running MPI graph benchmarks, so you create all the pairs of MPI and run them together. Using static routing, some pairs got almost 100% of the network bandwidth. Some pairs share the same link, so they got 50%, and some pairs got less. With adaptive routing, you get 96% network utilization. So you see there are people talking about new networks that might achieve 90% network utilization. Here you have InfiniBand on 9600 nodes with 96% network utilization using adaptive routing. So HDR InfiniBand, this is what we provide today. ConnectX-6 is the adapter, 200 gigabit per second, Gen 3, Gen 4. All the in-network computing elements such as tag matching, the ability to do emulations of PCI Express devices. So that's what we put here as NVMe emulation, but you can emulate other PCI Express devices. If you have ideas, we'll be happy to talk with you. There is block level encryptions and multiple other things for security perspective and so forth. From a switch side, all the switches have shield and sharp incorporated within the switches. There is the small 1U boxes with 40 ports of 200 or 80 ports of 100. And then there is the large chassis switches. I think Frontier has 6 of them, if I remember correctly, that provide 800 ports of 200 or 1600 ports of 100 in one chassis. We also brought a lot of telemetry or real-time telemetry into the switches, so you can actually get the buffer histograms and do latency analysis and more interesting things, and get more clear understanding of what's happening on the network side. Last part here is Bluefield. So Bluefield is a device that we released in beginning of 2018. And Bluefield, it's actually a combination. It's a system on a chip. So Bluefield takes the IP of the adapter. In this case, Bluefield 1 has the full ConnectX-5 inside. So everything that goes with ConnectX-5 exists in Bluefield. It also includes 16 cores of ARM A72 64-bit, 2 DDR4 channels, PCI Express switch, and a crypto engine into one silicon. Bluefield goes to multiple areas. It's not a server CPU. It's not meant to go there. It's not something that we're driving. It's not our area. This is where we're collaborating with Intel or AMD or IBM and ARM and so forth. But Bluefield goes into 2 main areas. One area is for embedded appliances that needs a strong network with RDMA and some compute to manage the box, such as NVMe appliances, for example, of JBOFs. Mellanox has a JBOF box just for proof of concepts and for people to play with. But there is multiple storage vendors that actually using Bluefield in order to build their own JBOFs. The more relevant part here, it's actually what we call smart NIC or smart adapter. So think about having Bluefield on as an adapter device, same as you plug ConnectX-5 or ConnectX-6 in every server. Now you have the same ConnectX capability, but with compute engines or actually compute cores on it. So you have a Linux machine within a Linux machine. And on those compute cores, you can run things in parallel of what's running on the main CPU. And this is where you can think about starting to break applications that run and run part of the workload on the main CPU. And actually, you can take some part of the workload and run it on the network CPUs and run those 2 in parallel. So there is some work in order to create APIs for smart devices like that enable us to actually break the workloads and do part on the CPU, part on the network itself. It also gives the ability to actually start playing with moving algorithms to the network. And then later down the road, we can move those algorithms to the ASIC itself. And the last part is security. So one of the main issues in security today is that you're running the security domain on the same application domain. So if someone got access to the CPU, then you get access to the data. What we're enabling with Bluefield actually is doing the security on the network. So we can do the encryption on the network itself, and once the data goes to the CPU or CPU memory is already encrypted. So if someone got access to the CPU, you can actually do nothing with the data. So that's another area. So overall, there is a great performance advantages getting from in-network computing. First, on the routing or adaptive routing, 96% network utilization, which I think is a great number. And then with Sharp, you can get much less or reduce latencies for reduction operations or any other data aggregation. But more important is you get flat latencies. So that's kind of the best scaling you can get. And then we see the nice impact of using Sharp on deep learning. So we are expecting to see 2x performance. We see 2x performance on some areas already. Shield is on the resiliency, and then very strong roadmap moving forward. We have 200 gigabit per second today in production in multiple systems out there. We are working on the 400 gig. So that's moving double the speeds, increasing the densities of network devices and so forth, and start to look even into the generation after. Look on XDR. So overall, on the HDR side, on the top 500 in June, we saw the first systems that were based on HDR. The highest ranked system build, or that was on the top 500, was actually Frontera. 8,000 nodes utilizing HDR. Mississippi State had 1,800 nodes, ranked 62. CSC had put the first phase, so they're building a multi-phase system. First phase, the small phase, the very, very small phase, was on the top 500. Tsukuba University built an interesting system combining FPGAs and GPUs on one platform. And then with Michigan and CDAC, which is using HDR for the National Supercomputing Program. And now there are more. I think there were announcements by some weather institutes in Europe. I think NCI in Australia already announced that they're building HDR with Dragonfly Plus. And we'll see more announcement on a very large scale system using HDR out there. So we see a good take on it as it provides kind of the best throughput on one side and the most sophisticated in-network computing capabilities. Thank you very much.